Hi, what I thought I'd do here tonight is play with a couple switches. These are configured in a special way. You can see there's a lot of cables between them, but really they're not a flat switch. This is a pair of 48 port SMC switches, and these ports are configured as pairs. So port number 1 over here is configured as a single 2-port switch with port number 3. Okay, only these 2 ports are configured as a switch on one VLAN inside here. Then the next pair of ports is configured as a completely isolated switch on a different VLAN. Okay, same with the bottom rows here, so that the pattern just kind of goes in pairs and continues all the way across. Same with the bottom switch itself. So what is this good for? Well, if you've got this black cable here feeding in a packet, that packet will enter the top switch on port number 1. It'll be switched internally and emerge on port number 3 here, take the cable all the way down to the bottom switch here. It'll enter the switch on port number 3 on the bottom. That's connected horizontally, so it'll leave the switch on port number 5 on the bottom, go up here, enter port number 5 on the top. These are connected now. Leave port number 7 and so on. So this will go down, this will go up, down, 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 up, and down. Okay, now once the packet gets here and enters this port, there's no other port for it to go to. These are just copies of the last 4 ports here. So this switch is configured vertically. Okay, so whatever goes in here will come out here. All right, so that'll go up and then back to going across. So this will go down on the blue cable, up, down, 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 up, and down on the last cable. Now when it enters the bottom here, port number 2 on the last cable of the bottom switch, again this is configured differently, so the top and bottom ports are actually switched together, not in a horizontal config, but in a vertical config. The port number 1 here, which is the top left, just like this guy here, is also blank, although you probably can't see it from that angle. So, what this entire stack allows me to do is pass a packet in through here and out through there, and it'll be subject to 48 switching hops, okay? And it'll be subject to 48 cable transitions. Okay, it'll have to go across these 48 cables, and it'll have to go across the corresponding 48 switches that tie all the cables together inside the silicon of these physical switches. Okay? So what I'm interested in studying here is the latency that's added by this kind of configuration. Let's say you wanted to deploy a network and it was using a large number of switches in series like this. 48 is kind of an extreme case, but it's really good for taking dividing and taking average measurements. So this is actually a really great setup for that. So what I'd like to do is take a measurement of just these switches and their switching latency. Okay. So in order to do that, I've got a PC over here, and it's got a little blue cable that feeds it Ethernet to the rest of the house. Okay. So what I'll do is I'll send some pings over this cable, which itself is connected to 3 other switches before it hits the server I'm going to ping. And there's latency added by those 3 switches. There's also latency added by the processor on here. There's latency added by the processor on the server. So all of that needs to be factored out so that the latency of this switch stack can be isolated in a measurement. Okay? So I'll take one latency reading here, I'll take another latency reading here, subtract them, and then I'll get the latency of just this switch stack. All right? So hopefully I can zoom in on the screen here. Oops. All right, I'll generate some 1500 byte ping packets. Okay, when you pass 1492 here, it actually generates 1500 byte packets. I'll send 100 of them, I'll send them every 0.1 seconds or 100 milliseconds to that IP address. And this is with this PC plugged directly into that simple 3-switch daisy chain, and then directly into the server. All right, so the baseline here is 363 microseconds, or 0.363 milliseconds for the round trip time just across the bare network, with all of the other latencies factored in, the PC switching time and all that. So now let me use this black wire here, which is plugged into port 1. I'll route that and patch it into the PC itself. There we go. And then I'll take the house network and plug it into port number 1 here. Perfect. All right, I'll do just one ping to make sure all the cam tables are good and we got ARP resolution, we're good. Okay, so let's take that measurement again, and this time maybe I'll actually show the lights during this. They're not super exciting, but they are kind of blinky, and anytime you can have blinking lights, that's cool. So yeah, this time clearly the switch stack is being used here. Those 48 are being traversed. All right, kind of hard to read the number here, so let me zoom in. Hopefully that's legible. So this is 1.82 milliseconds round trip time on average now. So quite a bit different from the, what was it, 0.363. Okay, so clearly a latency has been added, even though I'm using 1500 byte packets on both. Okay, so let's isolate that latency. This is just a math program, BC, so 1.82 minus 0. I believe it was 363. Let me just verify. Yeah, 363. Okay. So 1.457 milliseconds is the delta between those two measurements, which means that this switch stack on a round trip time added 1.457 milliseconds. Okay. Now that's just round trip time, so let's try and just get a single switch time. So first of all, let's divide that by 2 to get the forward latency time that's been added. Okay, so 0.7285 millisecond added across 48 switching hops in the forward direction only. Okay, now if I just wanted to get one switching hop's latency, I'd divide that by the 48 switching hops that were added to the signal path. And there we have a much more interesting number. 15 microseconds is basically the latency here that was added by inserting these 48 switches, and it was added in across a single switching hop, 15 microseconds. All right, so how does this compare with some theory? The number of bytes being transmitted here is roughly 1500. It's not exactly 1500 per frame, because the ping size here does not reflect Ethernet frame header size. It doesn't reflect the preamble size, doesn't reflect the frame check sequence, so there's a few extra bytes in there, but I won't worry about them. 1500 is a sufficiently large portion of each frame that it's pretty representative of the latency that's being added, or of the number of bits being transmitted. Okay, so if I wanted to transmit 1500 bytes, how many bits is that? So I'll multiply that by 8. So I'm moving 12 kilobits per frame per forward switch event. Okay. Now, how long does it take to transmit 12 kilobits at a gigabit? So that's 12 kilobits divided by 123, 123, 123. Okay, that's 1 billion bits per second. So 12 kilobits out of 1 gigabit And there we have the signaling time. And would you look at that? So the amount of time required to just get that packet payload on the wire, just to bang it out at gigabit speed, is 12 microseconds, okay, on a per hop basis. And the amount of time that was measured on a per forward hop basis, or per hop basis, doesn't matter, forward or reverse, was 15 microseconds. So we're pretty close to just the raw signaling speed of Ethernet. This also tells me that the processing latency on these switches is on the order of about 3 microseconds on a per hop basis. So that's not bad. If you're building large networks like this, well, they'll be really fragile if you lose a cable somewhere along the way. But if you can manage to get a handle on that problem, you can see it's totally workable. It will add some latency. Going from 363 microseconds round trip to 1.8 milliseconds is quite a degradation, but really 1.8 milliseconds is not that bad in terms of internet experience overall. So yeah, that's it. Thanks.